All right, hello kiddos. Welcome back to Mr. Forbes's calculus lessons. Woohoo! All right, so we are in let's see, unit. Well, I guess our unit 8, I guess, because we just finished up techniques of integration. So we've already learned what arc length was in this unit, and now we're on to our another second day of rectangular calculus here. So arc length, we're going to use arc length today to talk about something called surface area. Okay, and it's not too terrible. It's another formula, just like arc length. It's kind of how this chapter works. But let's try this warm up together. I think we have time to do the warm up, and I'd like to teach us something new. Maybe do one or two examples together. Okay. All right, number one says set up but do not evaluate. God, I love that question because it's just pretty much asking you to just do a formula or just set something up. It's no math involved in terms of equating anything. Set up but do not evaluate the integral that gives the length of the graph y equals the sine of the square root of x between x equals a and x equals b, where a and b are greater than 0. Okay. Well, it's just a formula. Okay, just remember the formula from yesterday. And remember, the only thing we really need to do to set this up is what y prime is, what the derivative of the function we're looking at. So let's just kind of quickly do that real quick. Derivative of sine is cosine, square root of x, and then multiply by the derivative of the inside, which would be 1/2 x to the negative 1/2. Okay? Or if you want to just simplify that up a little bit, make it look nice, you could say that right there. Okay, I just brought the x to the negative 1/2 down to the bottom of the fraction. Okay. Now, if I want to set up arc length, this is just a review of yesterday. Our length is equal to the integral from a to b, and it is the square root of 1 plus f prime squared. So if I want to go ahead and square everything from my f prime above here, that would be the cosine squared, square root of x, over 4, and then x squared, square root of x is x. So you could have left that as this entire thing squared if you wanted to, but I went ahead and simplified it down. So there you go. There's the setup. Yay. All right, and then the next one says the length of a curve from 1 to 4 is given by this. Okay. If the curve contains the point 1, 6, what is the equation of the original curve? Okay. This right here is arc length. Now, that's the formula that we learned. And what this is pretty much testing you on is that you're able to identify the original function from the arc length formula. Right? So pause the video, see if you can do it yourself. But here's the setup. Remember that the formula itself is the square root of 1, okay, plus f prime of x quantity squared dx. So how can I rewrite this to be in the form where we have f prime squared? All right, well, think about it. So we got integration 1 to 4. The square root of 1 plus, instead of 9x to the 4th, let's call that 3x squared squared. Okay, dx. So this is what the formula really looks like. And now we know that this inside that squared function, we know that's f prime. So I'm given that f prime of x is equal to 3x squared. Now, can I not solve for the original function from that? Can I not integrate this? F of x is going to be the integration of 3x squared, which is just x cubed, plus c. Well, we can actually solve for the c because we're given an initial point. So if I plug 1 into that, instead of equal to 6, you get that c is equal to 5. So my original function is x cubed plus 5. So there's a little recap of yesterday. Just understanding the formula and being able to do that. All right, let's keep going. This is another fun little warm-up problem that we'll probably try to do tomorrow together, or in class together. So You can kind of ignore this now. If you want to go through and try to do this on your own, you can, but it was just an old free response I thought was fun. So we can come back to that tomorrow as well. Okie dokie, here's the new stuff today. So this is on something called surface area, and it incorporates what we know about arc length as well. So this is pretty much another just day of formula. So it's a formula for the surface area of a solid of revolution. Okay. So we got two formulas. We got it whenever it's the surface area revolved around a horizontal line or around a vertical line. So just like when we were doing volume, okay? So this is similar to the idea of rotational volume, but we're going to be doing rotational surface area. So let me give an example of this first one here. So like, for instance, let's say I have this picture right here. Let's just start off with a generic, maybe square root function, something like that. Okay. And I'm thinking back to whenever we did rotational volume, we kind of talked about something similar as well, right? Okay, well, if I were to rotate this about maybe the x-axis here, okay, you know it's going to kind of reflect its shape right here, and it's going to make this kind of bad at this. No, it's not too bad actually. I'll take that. Okay, it's going to make that kind of like weird little dome-looking shape, right? Well, before what we learned in Calc AB was how to take the volume of this rotational shape. But now I'm not worried about the volume. I'm just worried about the two-dimensional area of the outer surface. So like just the outer part, not the whole volume. Just kind of what I'm shading right here, right? Well, it's pretty simple. So it's what it's doing is it's taking all of those circles' circumferences and adding them up. Instead of taking all the circles' areas and adding them up, like that would be for volume, it's taking all of the circumferences and adding them up. Okay? So whenever we did rotational volume, we dealt with pi r squared. Whenever we're going to be doing rotational surface area, we're going to be dealing with 2 pi r, which is not area but circumference. So it's taking all these circumferences and adding them up. Well, how do I figure out all of those circumferences of those circles? Well, if you think about it, I'm going to try to highlight this in blue. The circle's circumferences are just coming from that arc length. Okay. All right. So like for instance, the radius from here to here, that's the distance from my axis of revolution to my function. And if I want to know all of those arc lengths, okay, that's just going to be my heights. Okay. So this is essentially what we're doing. This is going to tell us the surface area. It's pretty much all of my circumferences times all of my heights. And that's going to add up all of those what's the word I'm looking for? Circumferences, right? Okay, well, if this is the formula that we're going to be dealing with right here, okay, since 2 pi is just a constant, 2 pi is always going to come out of the integral. A to B is just the distance from the leftmost point to the rightmost point. And then we're left with R and H. Okay, R of X is just going to be the distance between F and the axis of revolution, as you can see in the picture right here. Okay, and then the heights, okay, it's just going to be kind of our arc length. Okay, because think of this as kind of like a base times height scenario here. Okay, so how we figure out the heights here, okay, that's just going to be my arc length. Ta-da, that's it. Okay. So the setup's super easy. I mean, it's the same thing like for this other situation. Instead of, say we had the same picture, instead of rotating it around a horizontal line, we're rotating it around a vertical line. So it kind of makes this shape here. So we get this kind of shape right there. And it's the same thing as before. Okay, still 2 pi. R of y is now the distance between the function and the line of revolution. So like from like the outermost point to the line of revolution. And then the height is still going to be the arc length, but in terms of y. Okay. So if you didn't like the explanation, it's no big deal. It's just 2 equations, really. So just add this to your list of equations that you need to know. this and this. And yeah, that's about it. So let's look at a couple examples. Example 1. Find the area of the surface formed, so surface area, formed by revolving the graph of x cubed on the interval 0 to 1 about the x-axis. So before we start, let's just draw out the scenario. All right, x cubed from 0 to 1. So 0 cubed is 0, 1 cubed is 1. So, and we know kind of what the generic shape looks like. It's that right there. Okay. So I'm taking this little arc right here, and I'm rotating it about the x-axis. So it's going to kind of remake its shape on this side here. And it's going to have this kind of rotational shape, right? Okay. Now, so since this is rotating by a horizontal line, this is kind of like a top minus bottom deal. This is going to be that first equation. This is going to be a dx. Okay. All right. Well, as long as you have the formula for surface area, you're totally good. All right. R of x, right? X in this case, is the square root of 1 plus f prime of x squared dx. So just fill in the numbers, and you got your answer. So 2 pi going 0 to 1. R of x, remember, is just the difference. It's our radius, the difference between our function and the line of revolution. Well, our function is x cubed, and our line of revolution is 0, so that's just x cubed minus 0, or x cubed. Then we got the square root of 1 plus f prime of x. F prime of x is just 3x squared, the derivative of x cubed. So I'm going to put 3x squared dx. Yay! Okay. So the setup's not too terrible here. Now we're just going to simplify and integrate and just go on with our good life here. So it's 2 pi integration 0 to 1 of x cubed. Let's simplify on the inside as 1 plus 9x to the 4th dx. Okay? All right, so you got to figure out how to integrate here. Go down your list, see what works. I'm seeing that we have an inside as an x to the 4th and an outside as x cubed. So I'm thinking that u substitution is going to work pretty dang good for us. Like if I let u be 1 plus 9x to the 4th, du is going to be, what's that, 36x cubed dx. So we got 1 over 36 du equals x cubed dx. And yeah, that works out great because there's dx and there's x cubed. So what I'm left with is 2 pi. I can bring out the 1 over 36. Integration of. The x cubed and the dx go bye-bye. So I'm left with just the square root of u du. Right? And you know I'm a fan of u-bounds. That's how I like to teach it. That's how they like to use it on the final exam. So instead of saying 0 to 1, I'm going to use my u equation to change those to a u-bound. If I plug 0 into that, I get 1. And if I plug 1 into that, that's 1 plus 9 times 1, that's 10. Okay? All right, so let's just integrate this bad boy and solve. So we got, let's see, that's pi over 18. And then the integration of u is going to be, or u to the 1/2, isn't that just u to the 3/2, the 2/3 right here, evaluated from 1 to 10. So, you just plug 10 in, plug 1 in. I might combine these together. I believe that combines together as pi over 27. And then you have 10 to the 3/2 minus 1 to the 3/2, which is just 1. So my surface area is equal to that. That's units squared, I guess, because it is a two-dimensional area. Okay. Let's do one more together. Try to keep it as short as I can today. I'm not going to do all the examples. Let's try to do one more. It says find the area of the surface formed by revolving the graph x squared on the interval 0 to the square root of 2 about the y-axis. So there's the difference. Okay. If I were to draw this out, okay, we're looking at x squared. We're looking between 0 and the square root of 2. So if I plug a 0 into x squared, there's the 0. If I go over here to the square root of 2 and plug that into x squared, you just go up to 2. So I'm at this point right here. Well, I'm rotating this about the y-axis, so it's going to reflect the shape over here, and it's going to make that kind of, again, three-dimensional spiral-looking cone shape. Okay. And I'm curious about that surface area, right? I'm curious about what the area around the surface is going to look like. That's not bad. That's ugly, never mind. Okay. So because I'm going right to left here, right minus left here, and rotating about a vertical line, this is going to be a dy equation, meaning everything needs to be in terms of y. So let's go ahead and rewrite x squared in terms of y. If y equals x squared, then x equals the square root of y. And I know usually when we take the square root, it's plus or minus, but because we're looking at between 0 to the square root of 2, this part of it right here, that would be the positive square root of y piece of the graph. So I don't have to worry about that. And we can go ahead and figure out that x prime is 1/2 y to the negative 1. Okay. All right. So knowing all that, we can set up our surface area equation. But remember, it's going to be 2 pi, the integral, a to b, r of y in this case, okay? And then the arc length is 1 plus f prime of y dy, everything in terms of y. Okay? So surface area equals 2 pi, integral from, instead of a to b, okay, instead of a to b, it needs to be the lowest point to the highest point, right? Bottom to top. So the lowest point is at 0, and the highest point is at 2. It's going from 0 to 2. Okay, it's the y values, not the x values. All right. And then r of y, we already figured out, is the difference from my function to the line of revolution, which is the square root of y minus 0, or just the square root of y. And then we get the square root of 1 plus, instead of f prime, oh, I'm sorry, I should have wrote f prime squared here, I'm sorry. And instead of f prime y squared, it's going to be 1/2 y to the negative 1/2 squared, which I'm going to write as, I'm just going to go ahead and write as 1/2 square root of y quantity squared. We'll do this in a couple steps. Okay. Okay, so there's the setup. Now we're just going to go through and simplify. Okie doke. So let's first simplify down that squared inside the square root there. So that's going to be what? Just 1/4y? Now, we got to simplify this a little bit more before we can integrate it. But what I'm seeing, and hopefully you're seeing it too, we got a square root times the square root, meaning I can combine that to 1 square root. Right? So it's like I can, okay, so I'm going to have one big square root, and I can have y times 1 plus 1/4y. So if I distribute the y through, it's going to be y plus, and then y times 1/4y is just going to be 1/4, right? Because the y's are going to cancel. So that's kind of a benefit there of distributing. And I should be able to integrate this, honestly. I mean, you can do substitution to make the picture a little bit clearer, but I don't think it's going to really make it any different of a problem, right? All that's just going to do is just kind of help us visualize an easier integral. So it's going to be the square root of u du, and we can go ahead and change the bounds to u bounds if you want, right? We got a u equation. I can plug 0 into that and get 1/4. And I can plug 2 into that and get 2 plus 1/4, which I believe is 9/4. Because that would be 8/4 plus 1/4. Yeah, it's 9/4. All right, well, let's integrate it. So this is equal to 2 pi integral of. We know the integration of the square root of u is just 2/3 u to the 3/2. And we're evaluating from 1/4 to 9/4. And it's just the same as before. So I'll combine this together as 4 pi over 3. And then I'll have, let's see, 9/4 to the 3/2 minus 1/4 to the 3/2. And for the sake of time, we can just leave that unsimplified. It's calc inactive, so I'm good with you leaving it there. All right, so we went over what surface area was. We did an example of top minus bottom and an example of left minus right, the two different equations. I got 2 more examples that I'm going to do with you in class. And I was trying to keep this video as short as I could for you today. Hopefully you were okay with that. And I'm going to go ahead and end it. So you should have a good little intro into what we do in class. Okay. All righty, well, I'm done. And hope you have a great day. And I'll see y'all in class.